Welcome back to the office. We want to wrap up our example taking a look at the 8th roots of unity, the left cosets, right cosets, and now in this example, we're going to take a look at the multiplication table, rearranging it a little bit. Okay, so we're taking a look at, again, those 8th roots of unity, trying to observe what happens with our left and right cosets. I'm going to rearrange our multiplication table based on the cosets of this subgroup. So of course we have the coset of the group, the subgroup itself, 1 and zeta to the 4th, 1 and zeta to the 4th. Then we also had zeta and zeta to the 5th. Our next coset was zeta squared and zeta to the 6th. Zeta squared, zeta to the 6th. And then our last coset was zeta cubed and zeta to the 7th. Excellent. So we have our elements written out. And what now all I want to do is I want to rewrite the multiplication table based on this particular arrangement of the elements. Of course, this is a bit tedious and maybe a little bit annoying, but it's not the worst thing ever. We'll start filling it out and it's actually completed on the next page. So 1 times 1, of course, is 1. 1 times zeta to the 4th is zeta to the 4th. 1 times zeta is zeta. 1 times zeta to the 5th is zeta to the 5th, and so on. So zeta squared, zeta to the 6th, zeta cubed, zeta to the 7th. Same thing along this column, zeta to the 4th times 1 just gives us back zeta to the 4th, zeta, zeta to the 5th, zeta squared, zeta to the 6th, zeta cubed, and zeta to the 7th. Now I have to say, okay, well, what's zeta to the 4th times zeta to the 4th? And if you need to refer to the previous table, that's fine. Since it's commutative and we're working with these things where we're just adding exponents and taking modulo 8, it's not that bad. So zeta to the 4th gives us zeta to the 8th, which is just 1. Zeta to the 4th times zeta is zeta to the 5th. So adding 4 here, 5 plus 4 gives us 9. Mod 8 is 1. 4 plus 2 is 6. Mod 8 is still 6. 4 plus 6 is 10. Mod 8 is 2. 4 plus 3 is 7. Mod 8 is still 7. 4 plus 7 is 11. Mod 8, that's 3. Zeta times zeta to the 4th. See here, that's zeta to the 5th. 1 plus 1 is 2. 1 plus 5 is 6. 1 plus 2 is 3. 1 plus 6 is 7. 1 plus 3 is 4. 1 plus 7 is 8. Okay, pretty straightforward to fill in the remaining elements in a table. I would encourage you to do so. But to save a little bit of time, I've already done it. So here we have a completed table. And what I'd like to do is I would like to highlight for us the different cosets. So if I go ahead and I highlight our coset 1, 4, and then our coset zeta to the 6th. Actually, I don't want to do that yet. And that was to the 5th, of course. 1 and to the 4th. There we go. What I'd like to do is I'd like to highlight all of the appearances of those in our table. And notice that I end up with these squares. So 1, 1, zeta to the 4th, zeta to the 4th. I also have that over here. And I have it right here. And I have it right here. All right, let's see here. What's next? Let's grab onto a different color a moment. I'm going to grab onto blue, let's say. All right, so blue for zeta and zeta to the fifth. Zeta and zeta to the fifth. Well, now that, of course, appears right here and right here. It also appears right here and right here. Cool, I'm getting all these blocks. This is kind of fun. Next, let's do red. So 2 and 6. 2 and 6. Of course, that appears right there and right there. But it actually appears here as well. And yes, right here. And then finally, I'm going to go ahead and highlight. Let's use green, bright green. That's kind of fun. 3 and 7. Oops, let's see here. I made a mistake there. I didn't want that to be green. I wanted that to stay red. And I want to move on to the color green. There we are. Green, 3 and 7, 3 and 7, 3 and 7. 3 and 7. Of course, that's 3 and 7. So now if I were to say, let's look at this rather than being in terms of the individual elements zeta to a power, if I look at it simply as the elements yellow, blue, red, and green, then I know that when I combine blue and blue, I get red. When I combine red and blue, I get green. Cool, right? Fun. Notice that when I combine yellow with anything, I get that other color back. So I have this sort of identity color. Cool. This is a group. This is a group. This looks like a group. The elements are the set yellow, blue, red, and green. Fantastic, right? So I can observe this as a group where the elements are these individual colors. And this is isomorphic to, so the question is it isomorphic to Z4 or is it isomorphic to V? So Z4 is the cyclic group of order 4 and V is the Klein 4 group. The Klein 4 group, all of its elements are order 2. So anything squared gives me the identity. You'll notice that blue does not give me the identity. Red does not give me the identity. Rather, if I consider blue itself, I can take blue gives me red. Red gives me green. Green gives me yellow. Of course, yellow gives me back blue. So I actually see something that's cyclic. So this is isomorphic to the cyclic group of order 4, which is Z4. So that's pretty cool. We get this group of elements, right? This group of 4 elements isomorphic to Z4, where these elements are actually cosets. This idea is really phenomenal and it's very much of interest to us. It's something that we'll look at a little bit more later, but for now we want to be able to just kind of identify this pattern and whether or not we have it. So in this example, we do have the pattern. And our next example, what we'll find is that that pattern does not hold, and so we don't end up with something that acts like a group in terms of the cosets. We still get a nice split up of the group G, but those things don't act like group elements. So join me back here in the office to look at that additional sequence of examples.